Let's go now see how do we introduce, how we apply those learnings that we have done up to now for cell center. What we call also conventional finite volume method. And it is a method, of course, which uses the element as control volume. This is what comes from your grids generator, the elements. And then you have your unknown in the center of the element. So it's an element center, for cell center method. The unknowns, of course, are located at the center of the element in this case, which is, of course, the center of the control volume. I like to stress that the unknown is always in the center of the control volume. Doesn't matter if it's cell center or cell vertex. You can't have that. Here's my control volume, and here's my unknown. It's impossible, right? My unknown is always in the center of the control volume. But this kind of cell center or cell vertex, sometimes someone can think, cell vertex, the unknown is located at the vertex. Yes, at the vertex of the element, not of the control volume. The unknown is always in the center of the control volume. Let's just begin with our equation, and let's remember that to be conservative at discrete level, the conservation equation must be in divergence form before integration in the control volume. Doing so, as explained, and we talk about that in the first slide, the integration will be identically of performing a balance in the control volume. So this has to be clear for all finite volume analysts or specialists. I always have to have my conservation equations in divergence form, and then integrate the equation, and then this will represent is identically or of performing the balance of the property in the control volume. So if I integrate that equation in time, in space and time, which is in a divergence form, this is a divergence of advection, divergence diffusion. See, I could bring this to this side. And with the divergence of rho velocity phi minus gamma gradient of phi, and define that as a general flux. It's one flux, which is combining advection flux with diffusion flux. Then I will have my equation written like that. Plus this is a general flux which combines diffusion and advection. Combines diffusion and advection. Now what we have to do is to integrate this equation. Here is our control volume. You have to integrate in this control volume. Here's the neighboring control volumes. This is represented here is a general control volume. Can be 5 faces as shown here, or 7, 8. It doesn't matter. It can be any control volume. If you integrate that in a conservative expression. I repeat the equation there just to remember. And this is something which is already well known. If I integrate that in the control volume, I will have that. This is the time step here is appears in all the equation, then it's divided by here. Because when I integrate in time here, it disappears here. But when I integrate here, it keeps there. Then I divide and it's in this side. Rho times phi times dv is mass times phi. In the control volume, in the point P, minus, I'm integrating time, here is the backward differentiation which is applied. It could be using 3 levels, but we are using only 2 levels. So it's mass times phi in the level that I want to solve minus mass times phi in the previous time level. They are called old time level. This equation is a volumetric, is in a space equation. Using divergence theorem, you have turns to be velocity times scalar, the normal. So this is the flow rate. This is the flow rate. At every integration point, it's not showing here, but the integration points are here, there, 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 there. In the mid phases, in the mid of the phases. So this integration is the mass flow times phi at integration points. This integration, there is a vector, v. Here is a vector also. Gamma gradient of phi is a vector. So it's the same as there. So it's the vector, scalar, normal, they are the same. So this is measuring mass flow times phi, so is the advection flux. So this is gamma gradient of phi at the normal, so is the diffusive flux. And now happens what is important. So control volume, finite volume method is extremely easy method to develop. There's no difficulties at all. So it's physics. There is no strong mathematics. We can put a strong mathematics on that if we go to numerical analysis of the problem. But to create your conservation, your approximate equations, to get the linear system that you have to solve is so extremely easy and extremely with a physical understanding, which is easy to go through the method. In fact, we have 2 important things to be done when we integrate our equation. Is to specify the values of phi at the integration points and the gradients of phi at the integration points. Values of phi as integration points we already saw when we went through interpolation functions. Upstream, central differentiating, and so on, so on, so on. This is what is different now if we have unstructured grids. Because the gradient of phi needs to be determined. And I think I already talked about that, you know. I don't know if I was here in the class, but I know I made the simplification of the central differential scheme for Cartesian, for the one which expands the value from, I remember that. But here also, this is an integration point. This is a phi in P, This is a phi in E. What is an integration? The gradient is the phi dx, I, plus the phi dy j. This is the gradient of phi. The gradient of phi in this position, in this face, is just divided by some distance, dx. This is the gradient phi. But when you are here, it's the same. I'm here now. Here it's easy. You know? When I'm here in this face, will be phi n minus phi p. But if I'm there, my coordinate system is still here. The entity didn't change. I have still to find that. But now it's difficult. How do I calculate the phi dx here? I have no nodes in order to calculate the phi dx, because now I don't have such a nice organization, x, you know, normal and everything. And that's what I have to do there. I need the gradient of phi here, the gradient of phi here, the gradient of phi here and there, in all the IP positions, integration points for my control volume. That's the only difference. There's no other difference. Everything is the same for Cartesian and for unstructured grids. That's why I try to recall some important aspects of the method, which doesn't matter if it's cell-centered, cell-vertex, if it's Cartesian, if it is unstructured. The difference is just some expression that you cannot express with some facility or easiness as you can do in the Cartesian system. So now we need that, and the literature call that, so the gradient reconstruction method. And then, oh, there is one slide here just saying that we already we have seen this already. The phi, the variable at the integration points, if you choose among UDS, WDS, exponential, CDS, second order upstream, muscle, deferred correction, and so on. You choose. We already saw. You just pick up and put some that you choose according. Remember the physical consideration we have made concerning the interpolation function. Don't forget the reason for the appearance of numerical diffusion and numerical oscillation. So when you choose your interpolation function, remember what are you doing. Let me explain one problem. I used to explain this problem in order to see the danger in choosing some kind of interpolation functions if you don't see exactly what you are trying to solve physically. Imagine a problem where you have physical oscillations in your flow. The oscillations are physical oscillations, a real oscillation. If you go there with a measuring device, you are going to see some oscillations on your velocity field or temperature field or something like that. But you don't know that. You are trying to solve the problem. You don't know if the problem has oscillation or not, physical oscillation. And then you use an upstream differential scheme, first order, which dissipates difficult oscillations, smear the gradients. And then you have a physical problem. You don't know with the physical problem has physical oscillation because you didn't measure in the laboratory. So we are solving the problem. And then your upstream scheme may dampen, may eliminate all the oscillations. If you don't go to measure, you are going to get that solution as oh, there is no oscillation in my flow. But physically, there is. So this is a kind of problem. You have to know what I'm trying to look. Is there a chance of oscillations in this flow, physical oscillation? So take care and not use interpolation function which can kill your oscillations. The opposite is true also. Imagine you have a flow where there is no oscillation. And then you say, I'm going to use a higher order scheme, because higher order scheme is more accurate. Then you have second order or third order, or you can use quick, which is, and then you use quick, or use another higher order method, and then shows up oscillations in your problem. Then you say, oh, my problem has physical oscillation, but there was not physical oscillation. It was the result of the interpolation function which introduced some oscillations in your problem. So this kind of explanation tells you how care you should be in choosing the interpolation function according to what you want to solve. If you are trying to capturing oscillations, you have to tune up very well your scheme, your interpolation scheme. So that's what I want to remember that. Remember your physical problem. Try to see what I want to find in my problem. What is the physical characteristic of my problem? And then you use the correct interpolation function. At the end, you can check all that doing a very fine grid. Very fine grid. Then use central differential scheme, and then use a very fine grid that you are knowing that you are not getting oscillation and neither diffusion. So then, but then you have to go to a very fine grid to check. But be careful not using some mesh. Choose some mesh, choose some grid, choose some interpolation function, run the problem, and then you may see things that doesn't exist, you know. Be careful. Thank you. I'm just putting here two control volumes just to remember that normally grid generators gives you or triangular meshes in 2D or tetrahedrons in 3D. There is no which automatically, now you have to specify that as a user. There is no grid generators that puts triangles and prisms and hexas all together without you have specifying that. In that region, I want tetras. In that region, I want hexas. In that region, I want prisms. Normally, comes triangles in 2D, in tetrahedrons in 3D. And then you can use the triangles to create the control volume that we have used in several pictures here. This polygonal mesh is made of 1, 2, 3, 4, 5, 6, 7, 8 triangles. And then, why it's important to do that? What is advantage of doing that? You reduce enormously the number of unknowns in a matrix. Because if you use the control volume as the triangle or the tetra, which comes from the grid generation, there will be a lot of unknowns. Your matrix will be very large. And you have 3 integration points. If you do that, try to just imagine the number of control volumes you save. This one will be 1, there will be 8 integration points I have here, and 8 neighbors. But if I was going to use the triangles, original triangles will be 8 unknowns, right? Now we have only 1. So most commercial software which uses initially the grid generation with tetras in 3D or triangles in 2D, they have some kind of collecting, reuniting these basic elements in order to do a control volume for safe unknowns, in order to reduce the number of unknowns. Now this is the control volume from the grid generation. I have 3 neighbors, and I have 3 integration points in this control volume. There, when I make the reunion of several control volumes, get that, I will have 8 integration points, and it will be 8 neighboring control volumes which will be connected by my coefficients. The line of my matrix, which corresponds to this control volume, in this case we have 8 coefficients, 8 non-zeros in the line of this matrix. Yeah? So we call that a polygonal mesh. And then I just say, think about the number of unknowns, variables in your matrix that you save, transforming the original mesh to a polygonal mesh. And now we end up with the second important thing in our conservation equation. I'm repeating the conservation equation just to remember that this one we saw what to do, interpolation function, and now we have to do some interpolation function for the gradient phi. And then we saw there that it's not straightforward to do this gradient. And here the way we do, we call the gradient reconstruction methods. I really don't know why we call gradient reconstruction method. And in fact, we are calculating the gradient. You know, the word reconstruction here, I may be naive and not recognize it, but for me, what I'm going to do is to calculate the gradient. You know, I don't know why maybe in English the word reconstruction means. For me, it's calculation of the gradient. You know, and that's what we are going to do. In fact, calculate the gradient. Who is the gradient of phi? I need the gradient of phi where? In the integration points. I need the gradient phi in the integration point. And what we do, we calculate first the gradient of phi in the node, and then we put the gradient of phi, we expand the gradient of phi for the integration points. So here's small picture, it says, here we have the variables. Phi is here. And what we want to have is the gradient at the nodes. And then we will put the gradients at the integration points. How we can do that? So there is forms of doing that. There is ways, manners of doing that, which is you use Green-Gauss cell-based, Green-Gauss not-based, least square cell-based. The commercial software, they have all of them have these three methods to reconstruct the gradient. You know, let's have a look on those methods. And then I explained this, and I put the Cartesian system here and the general system there, just for us to know that what we are doing is the same. But we have some difficulties there because we don't have alignment of the grid points with X and Y. That's the reason. What we want to have is the gradient of phi in all these points. C1, C2, C3, C4. We have an area here. What says the Green-Gauss theorem? It says that the integral in the volume of the gradient of phi dV is the integral on the surface phi ds. This is transforming the volume integral to a surface integral. And the gradient of phi is approximated by 1 over v, the volume of the cell, the integral in the surface of phi ds, which comes from here, of course, right? Because what I'm doing, and you saying the gradient phi, I move out of the integral, then this is SV and the gradient phi. So this is Green-Gauss theorem. And the gradient of phi, therefore, is 1 over v, with the volume of the cell. The integration and the surface are replaced by a summation in all faces, of course. So it's phi times ds in each face. So I sweep from this one point to the other. Phi here times this distance, phi here times this distance, and this is a gradient of phi in this point P. Green-Gauss theorem. That's what you have to do. What we need in the Green-Gauss theorem, we need the values of phi at point, in this case, in this picture, point C, which is our integration point. We need phi here, phi here, phi here, phi here, and phi here. But I don't have. I have phi here. Now it's a matter of having phi here, there, there, and there, and there, trying to find phi at the integration points. That's what we want to do. And then, see, there was three methods there: cell-based, node-based, and least square. The cell-based means finding the phi at the integration point, at the face, using cell values. This is called cell-based. I'm using this value and this value to find the value here. And then face values determined using the neighboring cell values. This one plus this one gives you that and that and that. Let me do a parenthesis here. I always say that numerical techniques is a matter of you have, in order to finite volume techniques, you have to have the conservation equation, discrete form, then you integrate, then you have to have a good interpolation function for phi at the integration point, and then you have to have your gradient of phi, calculate the integration point. But it is a bunch of averaging that you do, because you are always with a discrete system. The key question is to have this average, which are the best ones. It doesn't violate your physics. This is important to take care. But there are easy approximations that have to be done, but you have to take care that this approximation doesn't go against your physics. And then, if I use this one for that, for this phase, this one, this is the stencil, the resulting stencil with, in order to calculate the gradient of phi in this point, you will need the variables around of all neighbors. It's easy. Huh? Requires the value of phi at the interfaces, so you have your neighboring contour volumes give you the values, because this is cell-based. If you go to a node-based, of course, you are always using the values of phi where they are. They are always in the center of the contour volume. But here is a kind of another arrangement. You use these three values to calculate one value there. Then you are going to use those three to calculate in this point. See there the picture? There, this one enters here, because if I use this one, and this one, I can put another arrow here, and there, another point here. The 2 points are showing there. So in order to find these two values, I use these 4. And then I will be using another ones, nah? And then I don't need in this vertex, I did in the middle. So I use this and that, and average in the middle. Then the phi is calculated in the middle of the face. That enters to my integral there to calculate the gradient phi. Huh? If you are going to do that, you are going to see that we'll use all the neighboring points, because if you are going to, for this one, then you need to do from that, and in all this will enter when I try to find all the phi around this contour volume. If in a triangular mesh, let's say I'm using my triangle as my contour volume. If it's a triangular mesh, or node based, this is the stencil. It will need to, because then I'm going here, that 3 points. This is the number of points that the number of contour volumes will give me the values to put in the vertices, and then do the average in the vertices to put in the middle of the cell. This is the stencil for the cell-based method. And this is the stencil for the node-based method. Because if it's cell-based, I use this one and this one to give here. This one and this one for here. And this one for here. If it's not based, then I will use this and that, put there and put there and put here. So see the difference. The cell-based uses only the 3 neighbors, and the node-based uses more contour volumes. It's obvious, because you first calculate in one side of the area, need some there. Then another side of there is some here. And then you average to the middle, you know. There's another method, which is the least square. Least square. How it works? You do a series expansion from point P here. Then you say that the pressure at this point is the pressure at point P, the pressure at this point, plus gradient of phi of P. P here is a general variable. R minus Rp, which is the size of the length of the domain. If I apply this series for all integration points here, like this one, I will involve 1, 2, 3, 4, 5 in this case. Then I will have let's have a look at P equal to PP, gradient of P. Let's see, then I'm going to put P minus, I'm just trying to put in one side such that this relation is here. And this, forget it, higher order. This relation, gradient of P, it's here. And this one and this one is here. So I apply this for every phase. In this case, I will have 5 equations, okay? Because I have 5 sides. And I apply the expansion in one and the other one. In this case, I will have 5. One there, here, 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 and there. And what is the unknown here? Is the gradient of P, of pressure of P, any variable. The gradient is derivative of P in relation to X, to Y, and Z. So I have 3 unknowns to be solved. But I have 5 equations. Did you get it? I have 5 equations because I applied the series expansion for each phase, 1, 2, 3, 4, 5. And in those equations, 3 unknowns appears. Gradient of P with X, with Y, and with Z. So I have 5 equations and 3 unknowns. So I have an overdetermined system. More equations than unknowns. So I have to do some minimum. That's why it is least square. Then we do some minimum, some criteria, and we determine the 3 gradients. The unknown. This is what I want. The gradient of phi, of phi or P in this case, the representation here. Phi is P here. And then I have this matrix, which has, let's say, in this case, 5 lines, and then I go at my unknowns, I have 3 lines. And my B, independent vector, 5. So I have to choose the best 3 equations of this system has 5 equations, right? That's what I have to do. I have a system with 5 equations, 3 unknowns. Then what you will say? What is the normal route to follow? Throw away the 2 equations which are the less important in this system. How you do that? Minimizing with some criteria. You eliminate the equations that are not the best one, you know. And then this is the least square. You can also have some weighting function, weighting value on this expansion. Just W1, W2, it's Wn. Every time you create this expansion here, you weighted the equation by some weighting that is 1 over the distance. If it's low, if it's a very let's say, non-uniform mesh, that you have one neighbor far away and the other one very close, you are waiting by this 1 over this distance. So this point is not going to play the same role with the same importance as the point which I have close. No? If I have if my stencil gives that, the importance of this point is higher than the importance of it, is larger. It's more important, this point, than that. So this is one distance. So you weight the equations 1 over d. So if d gets larger, larger, and larger, importance of this grid node disappear. You know, is the least square weighted by the 1 over the distance? You know, and then this is also used if you go to a software which solves the equations. You have the chance. You can choose cell-based, node-based, least square, which they are the 3 I remember. I don't know if there is another one. Now, the rationale is the same, doesn't change now, because of course we dealt only with 2D, but then everything is the same. Going from 2D to 3D, normally people that are writing papers, they say they do everything in 2D. Then the extension to 3D is straightforward. It's straightforward just in thinking, but when you go to do, it's a lot different, you know. But normally they say, there is one professor, I forgot his name. He said this is one of the big lies in numerical development, saying that the extension from 2D to 3D is straightforward. It can be straightforward mathematically, you know. When you are in 2D, you are calculating a gradient. It's gradient. In 3D, it doesn't change. It's a gradient, you know. But then you go there to calculate the gradient, then it's the job to do that. It's a lot more difficult. So, but then I'm saying everything is the same, but it's more difficult to implement. That's why in our lab we developed what we call the EbFVM, which is a library with entities, geometrical entities applied for dedicated to element-based. We want to see the element-based in order to give to developer all the details that are really, which makes the 2D to the 3D difficult, which is, because when you have one area in 2D and you have the vector here, it's easy to calculate the normal. But now if you have a surface here and your vector is here, then you have to know what is the area which is normal, you know, then it's painful to do all that. And if everyone that was going to develop some solver in 3D meshes, hybrid, sometimes triangle, tetras, hexas, if he's going to develop everything, then you are going to start again, you do all the same. The guys spend part of his time just programming the same stuff, everyone. That's why we try to develop the element-based finite volume library, which offers to the developer all the geometrical entities prepared, normals, vectors, and everything, and areas, such that the developer has to enter with his physical problem, with his discretization, choosing his interpolation function, choosing the method that he wants for solving the gradient, by the way, and then things becomes easy. But just, remember that going to 3D, polyhedral mesh in 3D, it's everything the same, but a lot more difficult to implement. That's why there is the library. So control volume, see the construction. This pyramid with a hexagonal basis, this is 6 tetrahedrons there. Can you recognize here 6 tetrahedrons with 4 faces each one? You put 6 tetrahedrons together, and then you have all another 5 or 6, and then you put all together, you get a polyhedral mesh. See the number of unknowns that you save if you would have 1, 2, 3 in the center of each tetra. If you would have one unknown, But this is then the construction of there are methods from tetrahedrons to obtain a polyhedral mesh like this one. And now, if it's cell-centered, then you have an integration point here, an integration point there, and then you are going to find the gradients of phi in all these points, the value of phi for the interpolation function, the value of phi, the gradient of phi in all these integration points. And then you do the balance. This is the control volume. So it's easy. There's no news in order to do that. So that's the and we have also one library for polyhedral grids, and then you have the control volume, the surfaces, the nodes which creates the surface, everything. So if you want to do some calculation, all the details, then it's easy to capture from the library and do your calculation. You don't need to start knowing the x, y, and z coordinates of the points, and then you do all the job. It's really time consuming, And you can have also hybrid grids. Then you use that in the transition. From an hexa, you can have a pyramid. And from that pyramid, each face of the pyramid, you can have a tetra. So it's one tetra comes here, another one, and then you go for your mesh with tetras. This is very important because if you want to solve aerodynamic problems, here's my profile. In aerodynamics, you are always, in turbulent flows, you have always the law of the wall. The law of the wall. It's what's happened close to the wall. In turbulence, you don't solve very, very, very near the wall. You have some point there with the first point that you are going to solve your equation, but from this point to the wall, you assume that you know the profile of the velocity. So this is the log wall, the law of the wall. And then this law of the wall that tells you how is the profile very near. It's better if you have a, let's say, the normal, and expressing this law of the wall in a coordinate system. This one would be the best one. A curvilinear coordinate system. It's not accurate if you have that and you start having triangles. Of course, I'm doing that in 2D, but it's 3D here, right? Triangles. Small triangles. Because I don't have I just some zoom here in order to. If I start with triangles, I have no points over this one. In order to, it has to be extremely fine, and then the triangles will not fit in the normal. It will be difficult to apply. You can apply, but can be less accurate if you would have a system like that. And then when you use unstructured grids, it's better to have a layer of axes. A layer of axes on the here, which is this one. And then a layer of axes. And then you put pyramids, which this book is one integral, is one element, and then comes a pyramid here, and then they attach tetras, and then you do all the grid with tetras. So it's difficult to draw here in 2D my pyramid, right? Yeah. But you have a layer of axes, and then your grid starts, and then you have a unstructured grid. But in the beginning, where everything happens in terms of physics, fluid flow, and to apply the turbulence quantities, there you put a layer of axes on the top of the axis, which the axis has a quadrangular surface. Then a pyramid fits there with 4 triangular faces, and each triangular face comes in tetra. Then you expand until you want to solve the problem. And in this layer of axes, it's similar to being using a curvilinear coordinate system. So you can apply this very well. So hybrid grids, general grids, can be used, in finite volume techniques for many problems. Well, final equation. The final equation, because after you have choose a interpolation function for phi, the integration points. Remember always, this interpolation function for phi connects with the unknowns nodes which are in the linear system. Phi in the linear system. Then you find the gradient of phi, which also connect to the neighboring phi's. Then this results in a linear system. This linear system has to be solved. It's going to be a matrix like that. Or there's a space here that I didn't put. Or here comes a simultaneous solution. Simultaneous. Can be solved one by one, linear system for a single variable. It can be segregated one by one, or it can be a simultaneous solution for U, V, W, and P, and then single equations, single system like that for the rest of the variable. And then you need to solve the system. You need to call, or you write, but this, numerical analysts, people who are doing simulation, they don't write this, the method for solving the linear system. We are going to talk about that. Iterative solution with a multi-grid acceleration is mandatory to attain CPU times, reasonable or acceptable CPU times. Now there is another job to be done, solving the linear systems. And it's mandatory, it's written there, it's mandatory to have a multi-grid method to accelerate the solution of your, because 60 to 70% of the total time that you spend in one simulation, you spend solving linear systems. It's time consuming. Then you have to put in parallel, you can parallelize your code. So then there is now, it's not in our scope to talk about methods of solving linear system, because it goes to it's linear algebra, and let's say the work of the numerical developer, let's say, finished here. Now he is going to call some routine, which solves linear system. And Petsky is one of the most used. I think it's okay. Yeah. Pets is a routine which has lots of numerical methods for solving linear system with multi-grid. Multi-grid is an acceleration. We are going to talk a little bit about multi-grid when we're going to speak about talk about element base, but the work finished here. Now it's calling routines which solves your linear system. Next class we start with element-based finite volume, because now we went through all the details which are the same for cell center and element base, and then we are going to do the geometrics of the element base. You are going to see that in element-based finite volume, we don't have this problem in calculating the gradient. The gradient is determined by another way. We'll see the details now of element-based. But you already could see that how simple it is since the beginning. You have the conservation equation, you integrate, you need the function at the integration point, you need the gradient of the function, you choose the interpolation functions, and then depending on the method you need to reconstruct the gradient or not, and then you have your linear system. Everything has to be based on physics, all the details. Interpolation function, everything has to be done on physics, especially when connected to the advection terms. If you have a diffusion, which is the gradient, doesn't matter, it's not so dangerous for the solution, because diffusion, gradient comes from the diffusion operator, and diffusion is elliptic, and diffusion is influenced for all sides, diffusion equation. So your interpolation can be always done with central differential scheme with simple averaging. The advection terms is different. You need always some direction of flow. In what influences the flow in the front is from the back and in some direction. And doing these things wrong gives rise to the numerical diffusion and numerical oscillation, which are the major problems in the numerical simulation, the major errors that we want to avoid them in the numerical simulation. See you on Wednesday. Okay? Thank you.